Okay, in this video we're going to take a look at a example singularity problem, and I'm going to work it out entirely by hand and symbolically, and then we're going to take a look at actually doing it using some numbers and using MathCAD to crunch the numbers. But this is out of the back of Shigley, Appendix 9, number 6, 9-6, out of the appendix, and it is a simply supported beam that has a single point load of magnitude F, but it's not centered. So it's a distance A from the left end and a distance B from the right hand end. And so to do this one, we first need to do the statics, and well, we eventually need to do the statics and get the reactions. So let's do that now. If I sum moments about this point labeled C, I'm going to be able to solve for reaction 1, because reaction 1 times the overall length L is going to, and then minus the point load F times the distance B from point C is equal to sum of moments equals 0. From this, R1 becomes a positive FB over L. And then summing moments about A, I'm going to have R2 times L in one direction. I'm going to have minus F times A in the other direction, R2 times L minus F times A. Set that those two moment terms equal to 0, and solve for R2. And R2 is F times A over L. So those are my two reactions. And now let's write our loading function using singularity functions. And so I will have as a loading function, that's my Q of X function, reaction number 1 times the proper singularity function for a point load. And if we were to look at the notes, and you can look at those for yourself, for a point load it says it use the minus 1 singularity function. And because it starts at the very beginning, I would typically have an x minus a kind of form right here, or an x minus something, but that something is 0. So we'll go ahead and put the 0 there for now. We'll get rid of it later. And that takes care of the reaction of the force here. Then I don't have another force until I get a distance a, and that's also a minus 1 singularity function. It's a point load as well, but it occurs at this location a. So it's a singularity function notation x minus a to the minus 1. And it's a negative sign because it's pointing downward. And then finally reaction number 2, written in singularity form, is reaction 2 magnitude times x minus L, because that load occurs at x equal L, so x minus L. And it's a minus 1 power singularity function. That finishes our Q function. Now, the integration for the next two terms is utterly trivial. I simply rewrite this thing and I raise all the minus 1 powers to 0 powers. And the next integration is equally trivial because I raise all these 0 powers to a positive 1 power. Now, the next integration is almost trivial, but since I'm going to raise the 1 power when I want to integrate this singularity function to the first power, it's will become a singularity function to the second power divided by 2. So all of these first powers become power 2, but I divide by 2. That 1 becomes a 2, but I divide by 2. This 1 becomes a 2, but I divide by 2. And now that I've gotten into my slope function, I will never really care about this. Matter of fact, the only place I really care about this is if I were going to plot the load function, and we'll do that in MathCAD in another document, then this term does have a visible effect. If I plot the shear function diagram, this term has a visible effect. But by the time I get through the moment term, this term no longer has a visible effect, and this term would not have a visible effect because I'm going to stop the problem at x equal L, and this term doesn't turn on until x becomes L. So this term I'm going to start ignoring now. But I have a constant of integration because I've reached the point where I need it. The power of the statics have run out. So I need that constant of integration. And then I'm going to integrate this function, and all of the 2 powers will promote to a 3 power. But when I promote to a 3, I need to divide by 3. But there was already a divide by 2 there, so divide by 2 combined with a divide by 3 would be a divide by 6 and a 6. And this term has gone away. Integrating the C1, I get C1x, and there's another constant of integration. So the power of the singularity function so far is to let me speed through these integrations without worrying about piecewise integration. Now I need to deal with my boundary conditions. And for this particular beam, I know that at the left-hand end, the deflection is 0. I also know that at the right-hand end, the deflection is 0. So I'll use those two. So at x equals 0, EIY is 0. At x equals L, EIY is 0. And at x equals 0, if I plug in x equals 0 everywhere, I'm going to get 0 on the left-hand side. I'm going to get a 0 from this term. X equals 0 does not enable this term. This term does not turn on. And x equals 0 here is 0. The only thing that's left that's not 0 is the C2. Therefore, C2 is 0. Again, very important. X minus 0, this term turns on at 0, just barely, but it's equal to 0. This term doesn't turn on, so that's equal to 0. That one does. Now, at x equal L, my deflection is also 0 at the other end. And so I'll take my EIY equation and I'll set this term to 0. This term becomes the R1 over L minus 0. This term becomes an L minus A term. X is equal to L here, and the C2 I've already set equal to 0. And this singularity function L minus 0 cubed simply becomes an L cubed because it's on when L equals 0, is bigger than 0. And I'm not subtracting anything, I'm subtracting 0. This term becomes L cubed. This term becomes L minus A cubed without the singularity function brackets because L is a constant and bigger than A. From this, I can solve for C1, and it's going to be a minus 1 over L times these two terms, which was the R1 over 6 L cubed, and then minus F over 6 L minus A, regular parenthesis cubed. Okay, or if I bring the L inside, that's become an L squared, and that's going to, in the denominator here, will become a 6L. And so this was going to be a minus outside the parentheses from that minus sign. Positive sign here, negative sign there. So taking the C1 and plugging that in right here in my EIY equation, I have everything I had before, which is the first two terms, right here and right here, unchanged, okay, plus my C1, but my C1 has a minus sign, so R1L squared over 6Y. If I take my C1, but I'm going to be multiplying it by, let's see, I'm going to be multiplying it by X. So C1 is R1L squared X, R1L squared over 6. This becomes R1L squared X over 6 because I'm multiplying by X right there. You can't see that. Sorry about that. Where'd my finger go? You actually have not been able to see a lot of what I just said. I maybe should stop the video, but I'm not going to. If you got frustrated, here are the boundary conditions. You might want to just pause it right there. Remember what I said. At x equals 0, we plug stuff into the equation here, and everything with C2 is 0, therefore C2 is 0. At x equal L, we plug in L here, we plug in x equal L everywhere, and doing that we can solve for C1, and C1 is these two terms divided by that L, so C1, these two terms, divided by L, and with a sign change because everything went over to the other side, and then simplifying trivially. Now that I have C1, I plug it into that spot right there, and I have my new slightly expanded equation, my first two terms, and these terms right here are C1 times X. But R1 showing up in here probably ought to be written in terms of the boundary conditions, which is R1 is equal to FB over L, or it's F times L minus A over L, because B is L minus A. You can write it either way. So now plugging in the definition of R1 right here, I get this equation. I just suggest you pause and stare at it, not too much to say about it. I just plugged in R1 having this definition into two different spots, here and here. And I just followed through the algebra. And then I noticed this FL minus A term showing up in a lot of places, not everywhere, okay? And it's an FL minus A over 6L. So I just pull that FL minus A over 6L out. So I'm doing a little bit of algebraic simplification. And then from this term, I'm left with an x cubed. To make this one work out, this has to be an L over L minus A times the singularity function. And then this one has the L squared x remaining. And this one had, let's see, an L minus A squared, because I pulled one of the L minus A's out all the way to here. And so it leaves behind an L minus A squared times x. So that's my deflection function. And that's the entire deflection function. At this point, I can stop right there. That's enough. But what I want to do is actually break it into two pieces. What's going to be true when x is less than a, and what's going to be true when x is greater than a. And so, let's take a look at that equation. And I'm going to call it EIY1 of x, which is the equation that's true when x is less than a. And what I make note of is that a term disappears. When x is less than a, going back to this very bottom term, I still have a singularity function left in here. And this singularity function is 0 when x is less than a. So I only have this term, and that term. And so that would be the stuff outside. But I also notice I can pull an x out of all the remaining terms. So this becomes FL minus A times x over 6L, leaving behind out of, let's move everything up a little bit. Since I pulled the x out, it leaves behind an x squared. It leaves behind, let's see, and, oh, this term disappeared. This one leaves behind the L squared when I pull out the x, and this one leaves behind an L minus A squared when I pull out the x. But L minus A is B. L minus A is B. So rewriting this thing, I get EIY in region 1, where again, x is less than A. Let's see. FB x, oh, L minus A becomes B there. L minus A here becomes L minus A squared becomes B squared. So this becomes, I was looking for my L minus A. FBX over 6L times x squared minus L squared plus B squared. And if you go to the appendix for beam number 6, you will see that this is an exact match of what they have in the back of the book. So this is the same as the back of the book. Now what I want to do is go back to my general EIY equation and say now that x is going to be greater than a. When that's true, this becomes x minus a. This term turns on. And while that's true, x is greater than a. As long as that's true, I can turn those into parentheses. So this term comes back alive. And so my EIY2, when x is greater than a, that's why I call it my term equation number 2, is my original equation, f times L minus a over 6L. And everything that I had in this equation here is simply copied down. Everything is copied down. If I want to, I can still do the substitution that b is equal to L minus a. So this becomes an FB over 6L. And this L minus a becomes a b. So this becomes a minus L over b, minus L over b. Nothing else really changes. This looks different from the back of the book. Move this up a little bit. And again, I'll point out that this B replaced L minus A there. This L minus A was turned into a B. Otherwise, it's pretty much the equation that was written at the bottom of the previous page. As I said, it looks different from the back of the book, but it's equivalent because I have checked it with MathCAD. And the equation here and the equation in the back of the book is exactly the same answers. I could attempt to do the algebra to turn this into the equation in the back of the book, and I'm not going to. Okay, so that is singularity function carried all the way through and achieving two different equations for the two different regions of this beam. Just a very quick summary again. Oops, something. Picture the beam, do the statics, write the Q function, integrate, write the V function, integrate, get the moment function. Okay, don't need any constant of integration yet. When I get to the EI theta, I bring in a constant of integration. And when I get to the E, then I do the EIY, and I get another constant of integration. Use boundary conditions to solve for the constants. Plug the constants in. Get a general equation that involves the singularity function, and we could stop right now, as long as we always, when we do this calculation, interpret depending on the value of x. If x is less than the value of a, this term's 0. As soon as x becomes equal to or greater than a, then this term becomes alive, and it becomes x minus a cubed. So this equation is true throughout, but with a little bit of algebra. In region 1, where x is less than a, it can be turned into that. It matches the book. And in region 2, where x is greater than a, it turns into that, which really means the x minus a cubed just becomes alive. It turns on. And I didn't simplify that any further. And that's singularity function video.